Hello friends, welcome you all to the session 19 of form based development. So in this session we would cover the interrupt processing in detail. Okay, so we are not talking about exception handling, we are talking about IRQ or FAQ. Okay, and what are the different schemes that can be supported. Okay, and then we will touch upon two kinds of handlers. Okay, I will tell you a sample interrupt handlers implementation, and then we will go through that in detail how it is implemented. Okay, so the scope of this discussion is understand what are the different schemes available. Okay, and then we will see two implementations of them. Okay, and I leave the remaining thing as an exercise. Okay, they are available in the reference book that I have mentioned, ARM Systems Developers Guide. Okay, they have given in that book there are some sample code implemented for the remaining interrupt handlers. I urge you to go through them. Okay, at your leisure. But this going through this lecture and understanding these two implementations will help you know how it is implemented to understand clearly, and then you will be able to follow with the remaining schemes. Okay, follow up with the remaining schemes. Very good. So let us see. ISR is interrupt service routine. There are two levels normally in handling the interrupt. Okay, I'll explain you with an example. How not typically some implementations are done in the real life scenario. Okay, so that you understand what do I mean by first level and second level. So the interrupt handlers are divided into two parts. Okay, one is the first level. So after the interrupt has been recognized and after it has been found which device is interrupting, then there are two levels of handling them. Okay, based on the device and based on the data that comes into the processor. So the first handler is called hard and fast interrupt handlers. Why do we say in a typical real time scenarios we say hard real time and soft real time. Okay, hard real time means it is very time sensitive and it needs to be processed within a fixed time duration, and any latency in handling them may be troublesome. Okay, you may have a failure or catastrophic failure if the timeline is not met. So that's what is called hard real time, and soft real time is something which can be done. Even if it is delayed, there is no not much of catastrophic changes, but maybe a degradation in the performance is expected. So the same line, the handling of interrupts also divided into hard and soft, or fast and slow. Okay, so this is the first level needs to be handled within some time gap. Okay, otherwise the data will be lost, and if it is a very critical data, then it may be a catastrophic failure from the system perspective. But soft means the second level handling could be delayed and it can be done. Once this is done on time, this can be little bit delayed, no issues. Okay, so it is not very time critical. So basically the interrupt handling is divided based on these two functions, and then we put most critical things to be done into the first level handling, and then the remaining processing involved which can accept some kind of a delay could be put into the interrupt service routine, which is the second level. Okay, so the naming is different. So what you should remember is the first level handling is the most critical thing which needs to be done with a limited time gap, and then the second level could be a longer processing, and it can take sufficiently a long time. Sufficiently in the sense it's not in terms of seconds, it must be some milliseconds or less than that, but you can defer this time allotted for this particular processing, you can defer it little bit and it is not very time critical. So let me give you an example. Okay. So this is the processor. Okay. Assume there is some interrupt controller. Okay. I call it as IC to simplify. So we are going to be looking at only IRQ input. Okay. Similar thing is done in FIQ. Only thing is normally the FIQ is directly connected to the processor. Okay. Not through any controller. Okay. I'll tell you what is the function of interrupt controller. We will maybe when I am talking about peripherals, we will touch upon this little bit to tell you what it exactly this coprocessor or a module does. It's another hardware module which can be connected to. So a IRQ input is here. Okay. So some of the peripherals, it could be, I can call it as some peripheral 1 and then peripheral 2. Multiple peripherals can be connected to the controller and then it will generate one interrupt to the processor which could be connected to IRQ. Okay. So as you are aware, processor has only two inputs to accept interrupts from external entity. So it is IRQ and FIQ, and you are all very clear now that FIQ has a higher priority than IRQ. So processor has its own priority among these exceptions and interrupts. So there are other data prefetch and then prefetch data instruction exception and then data abort, and then there is a reset pin, right? Reset. There are so many interrupts. The reset could be a direct input, and this aborts are handled internally. That means it can be generated based on the instruction being executed. Okay, during the when it is accessing the memory, right? So it has got its own priority among these aborts and then the interrupts that are coming in. So as you are aware, reset is the most highest priority, and then data abort comes, then fast interrupt FIQ, then IRQ. Okay, that is the order in which the interrupts are processed. So first is reset. Just to recap on that, reset. Okay, and then we have data abort. This is during data access to memory. If the exception is coming, then that will be given a higher priority, and then the rest is this will be FIQ. Okay, FIQ interrupt will be handled, and then IRQ. So this is the relative priority that processor gives interrupt. And you can decide selectively to enable some interrupt or mask some interrupts, and then give different priority to them, and then you can even configure it for level trigger or edge trigger. Those are so many things which are there to configure this interrupt controller, how it has to process the input coming from different processors. So individually, you may wonder what are the different peripherals that are possible. There are UART there, and then USB controller could be there. UART is a serial controller, okay, and then there can be a different disk can be connected to this, interrupt. There are so many ways you can timers can be connected. So the semi peripherals can be connected to this, and then they will the interrupt controller will prioritize them, and then they will generate an interrupt to this. Now when the IRQ handling happens, okay, IRQ, so when this interrupt happens, the processor may not know which device has interrupted if it is coming to a controller. So what will it do? The first level, it will try to find out which, first level, it will try to find out which device is interrupting, and then it will read that device. Okay, some device is there, suppose some data is waiting, it will read it from there and then keep it in a memory. The processor will keep it in the memory and then defer the processing to the second level. Okay, so first level is only to do the minimum work required as soon as the interrupt is generated, whenever it is being processed. Okay, IRQ is generated, and then this is the ARM processor. So whenever it is generated, and the ARM processor, when it gets a time, because there is no other FAQ or data abort or reset pending, then it will come and service this interrupt, and then on the first level handling, it will do what is minimum required to satisfy the device. That means, okay, if it has to be read from the device and then put into the memory, it will do. Okay, so or it has to inform back to say that, okay, you continue with the processing of next thing, and then it will defer the processing, further processing, to the second level of interrupt handling. Now why are we dividing this into two? Because after this first level is done, we can re-enable this particular device which has generated originally the interrupt. In fact, even we can re-enable the IRQ itself, so that the next device which is in the priority may be coming, and then it may be interrupted, and then IRQ will be generated, and then you will have that service routine coming up. So basically what happens is, after the first level handling, we want to re-enable the interrupt. So while handling the second level handling in interrupt, we want to keep this first level open, so that the processor is not blocked until this longer processing is completed. Okay, that is the purpose of this. So that typical for a real time scenario, this is very much required. Now you may wonder, can I have an example for this? Okay, okay, let me tell you some example. Okay, this is becoming very difficult to rub it. Okay, okay, let us see one example. Suppose you have a serial port. Okay, this is UART, asynchronous, so universal asynchronous receive transmit. Okay, so basically this is a serial port controller, a PC. Okay, you are connecting through RS232, assume. Okay, a serial protocol which you may be aware. So there are two inputs. Okay, one, okay, from the UART perspective, TXT is descending it to PC, and then from this RXT is input to the UART. Okay, so this is connected to the interrupt controller, and that in turn is connected to the ARM processor. Okay, through IRQ pull input. Now you are sitting in a PC, and then you are trying to give a command. Okay, let us give a scenario. Okay, you are here. Okay, you are giving a command. Okay, maybe read memory. Okay, there is a debugger or some other your own monitor running here in the ARM processor, which can read from the memory, and then contents can be sent to the PC, and then you can display, you can see the contents in the memory in the PC. Okay, now basically what are we trying to do? We are running some program in the ARM processor, and then we have connected a UART, which is a serial port controller, which you can configure it for some particular baud rate, and then particular bit configuration, parity 8-bit or 9-bit. Okay, and then parity is even or odd parity, and then baud rate you decide, and then the same configuration you do it on the PC side. So these two talk to each other through a serial port. Now we are sending a command, an ASCII command. Okay, maybe it may say that read mem. Okay, read mem, and then you will say that from 200, okay, hyphen 300. Okay, assume that it is an hexadecimal, and then carriage data. So what happens when this command is given? The monitor which is running will wait for this complete command to be received from the PC. So it will read one character at a time, or then D, then mem, and then it will understand the complete command is given, the carriage return is given, then it will assume that, okay, complete command is given, then this processing takes place here. to look at the values what is given, and then whether it is a valid command or not. Then if it is a valid command, perform the job. Maybe it will initiate another task or something to do the job. All that may not be handled in the handler, interrupt handler. But there are two things to be done. One is first read these characters as soon as they are received by this UART. Okay, it will be in a receive buffer. One character may be there. Then it will interrupt the controller, and then interrupt controller, based on the priority of other devices connected to it, it may interrupt the processor with the IRQ input. Then the processor comes and then executes the first level of handling. That is, where is it? Okay, this is the first level of interrupt handling. So it will read these characters first and put it in a buffer, command buffer or something inside. Okay, and then it will check whether it is a carriage written or not. Maybe 0 A, no A or D. Okay, this, if you remember, these two are the carriage written and line feed. So one of this may be a terminator to say that the complete command is given. So based on that, the first level interrupt handler can inform the second level handler to say that complete command is received. Now the second level handler can come into play. So you can imagine how frequently this will be executed compared to this. Until the whole command is received, this will not be executed, right? For individual characters, it won't be executed. Only when the complete command is given, this is executed, but it will take some sufficiently a longer time to execute, correct? So now itself we have seen a example where a first level handling and second level handling is required in the interrupts. Okay, this is a typical one example in a real life scenario where you may have to split your handling of interrupt in two different functions, and then perform the first job, copying the character from the interrupt handle, peripheral, and then copying it to the memory, and then complete command is received, then call this function to run the command. Okay, so this will be the second level of processing of serial port interrupt. Okay, so I think this much of introduction is enough. So let us see how we will be implementing it in a real life scenario. Okay, good. I hope that is clear to you. So this is a deferred procedure call which will be handled in the second level. Okay, fine. Now I am giving you differences based on what I explained you through a serial port. You should be able to appreciate these differences. So this implements a minimum platform specific interrupt handling similar to interrupt routines. That means receiving a character from the device, okay, and then copying it into the memory is a simplest minimum platform specific job. And then implements long interrupt processing. That means processing the command is done by this second level. Okay. Intent is to quickly service the interrupt, correct? And then this is deferred job is handled there. Here record the platform specific critical information which is only available at the time of the interrupt. So if you don't read the character which was received and then you enable the interrupt, the serial, if you say the UART can receive the next character, that will be overwritten. So you have to copy that into the memory before enabling it. So the minimum platform specific job in terms of serial port, it is what I explained, and it could be different things for different peripherals. So and then perform further processing here. Schedule the execution of SLA. So who does the scheduling of SLA? The first level handling. Because once the command is completely received, then only this is scheduled. Okay. Otherwise, second level may be deferred. It is not that always the second level will be executed for every first level interrupt. Okay. And then if it is re-entered, what I mean by re-entered, the interrupt handling could be, you can enable the interrupt while you are handling the interrupt. Okay. So the same interrupt is re-enabled. So that during that time some same or higher priority interrupts can come. So no, actually we are enabling this re-entrancy by dividing this into two functions, and then normally during the second level interrupt handling, the interrupt is enabled. So partially sometimes we may enable it during the first level itself. That is the kind of a schedule, scheme, handling scheme. Or if you are handling it, if you are not enabling it here, the second level you need to enable it. Okay, because it is going to be a longer processing, so we can't afford the interrupt to be waiting for second level also to be completed. So that is the reason of splitting it. But there may be some occasions where you enable it in the first level itself. Okay, that is another way of handling it. I will explain you. So programmers move maximum processing to this level and minimize the execution time of the first level. Okay, that is the difference. I hope this is very clear to you from the example that I gave you, serial port interrupt. Very good. Now let us see what are the different kinds of handlers. Okay, first I am touching upon the non-nested interrupt handler. This is the simplest handler. Okay, non-nested in the sense, while the handling of particular interrupt is, suppose you are handling the IRQ. Okay, the processor, the IRQ handler is inside the IRQ handler. Another IRQ interrupt is not enabled. Okay, that is what is non-nested. It is not nested. So let me erase this. Okay, this arrow has come inside. Not a problem. So SPSR. This is SPSR of the mode. Here, if suppose I am taking IRQ as an example, this will be IRQ. So when the interrupt happens, okay. So what is the sequence of operations? I have already explained to you. Okay. Maybe let me go back to. So just to recap. Okay. This is the device. Okay. And this is ARM. It is executing some instruction. I am doing it again to just recap on, to make you all ready for looking at the code that I am going to show in this class. Okay, so device is interrupting it. Assume that in this case I am just connecting the device directly to IRQ to simplify the scenario. So it is, the program is at 200 and it is executing it. Okay, assume that it is in ARM state. Okay, PC will be at 208. All of you are aware that it is +8 now because of the pipeline. Okay, so this is the instruction which is being executed. It could be any instruction, doesn't matter, because you cannot decide when the interrupt will come on, when you are executing the instruction. So it may be any instruction. So the processor, what does it do? It will first finish the instruction which is being executed. That is, there are different stages, right? 3 stages are there. Whatever instruction is there in the execute stage, it will be completed. Okay. At the end of the execution, the processor checks for IRQ input, FAQ input, reset input, anything is there or not. Okay, it will be checking, polling these bits. Okay, so once it encounters that okay, IRQ is there, then it will not bring the decoded instruction into the execute stage. Now it knows that okay, I need to handle the IRQ, so let me abandon this. So it can easily afford to abandon because it is not being executed. So anything that is supposed to be done by these instructions are not reflected in the register file. Okay, register file is not affected by any of these instructions. Okay, it is all inside the pipeline. So we can defer the execution of these 2 instructions and then handle the interrupt, and then afterwards you can start executing from here. So from the programmer perspective, you will not see any difference at all because of the interrupt happen. Okay, so that is the reason why the execute stage is completed. Because if suppose the processor decides to process the interrupt in the middle of execution, what I mean by middle of execution, the execution could be a LDM or STM, right? That is the maximum cycle it takes, multiple register load or multiple register store. So it would have, it is the ARM is interacting with the memory and then trying to load or store some values. So if halfway through, if it interrupts processor, then the register contents are indeterministic. Now the half of the registers are with the new value, but rest of the half is old value. And if you allow the interrupt handling to go in between the execution, then the stability is affected. So you cannot restart this instruction because you are halfway through you are executed, but you cannot start with this next instruction also because this is not completed fully. So to avoid all that confusion, what any processor does is, it will complete the execution of the particular instruction. Okay, complete it and then defer these instructions which are in the decode stage and the fetch stage, and then go and service the interrupt. So now what happens? It has completed the 200 execution. Then what does it do? It has to keep this information of register file and CPSR in a safe place. So which is the safe place? The bank registers are the safe place. So IRQ has come. So it will go to IRQ's bank registers, and then it will copy the CPSR into SPSR. Automatically the processor does. No, we are not writing any code. and then it will copy this, whatever is the PC value. This is the PC value. It will put it in this R14, and as you said, this is R13. These are the bank register. This, so later on, okay, I am not right now using the stack. Remember that the stack is there, and then what will we do? So the processor could be in ARM state or it could be in thumb state when this interrupt was generated. Okay, the processor may be executing it ARM instruction or thumb instruction. So based on that, but you remember that the interrupt handling is done only in ARM state. So it will change. If it is a thumb state, it will change to ARM state. Okay, and then what it will do? It will, okay. Now the next sequence will be PC will be loaded with the, okay, the IVT interrupt vector table meant for IRQ, that whatever is the address it will put into the PC, and then mode it will change it to IRQ mode, okay, and then it will start executing from the vector table. So IRQ it will go, it will be a branch there, so it will branch some interrupt handler, then interrupt handler comes. So this much of job is done. So this is the first one, and then this is also done together, and then changing the thumb mode to ARM mode is done here, and then it goes to the interrupt vector table, okay, and then goes to the interrupt handler, starts executing the handler. So in this case, till this point, a handler has not come, all the job is done. Now what happens after the handler is done? It will come back to the, it should come back to the next instruction to be executed. So the handler has to take care of whatever the PC is loaded. It should -4 it should do, so that it comes here, and then it should restore this value into CPSR, and then it should restore the return address anyway is here, so it will come here, that will be put into PC, right, -4 will be done into PC, and then starts executing from here. So from the user perspective, in between these two instructions, a lot of things have happened, but as a user you may not know because you are not seeing any change in the register file or in the CPSR or any other execution. So the interrupt has come in between without affecting our normal flow of execution. I hope this is very clear to you. I will try to explain this again so that you get back. Okay, let us go back to our. So this is what is done here. Okay, I will not explain this whole thing. It is what is done. Then the save context. Okay, this is because the handler also needs to use some registers, right? If it is using some registers, it should make sure that it is saved here, because you don't know when the handler and the interrupt has happened, these registers may be in use. You have to assume that all registers are in use. So the user program is using it. So you have to make sure that the handler saves the registers of the previous content and then uses them in the handler, and then after you perform the handling job, you restore the context. Handler does the restoring of context, and then it does whatever I explained you just now, and then return to the task which was executed. So this is the flow normally done. It doesn't matter whether it's for IRQ or FIQ. Okay. And then now the question is, here in the non-nested case, we are not enabling the interrupt throughout the case. Okay. Whenever we are doing this, we are not enabling the interrupt. So only one interrupt can be served till this whole thing is completed. Okay, up to this point. Okay, when it goes back to the return task, then only the IRQ is enabled. This is what is called non-nested. Okay, now let us see what I mean by this is not suitable for complex embedded system. Why? Because sometimes the processing may be longer, because we are trying to do the first level as well as the second level here. Please remember, first level as well as second level is being done without enabling the interrupt. That is what is called non-nested. That means I told you the second level could be a longer processing little bit compared to first level. So during this time, if you don't enable the interrupt, then we are unnecessarily delaying the processing of any interrupt that would come from different devices because of processing this interrupt. So which is not suitable for a complex embedded systems. Okay. Now next level of handling is nested interrupt. Now what happens in a nested interrupt? One simple change. This is same. Okay. This level is same. This is same. Only difference is even the saving of context, everything is same. Only thing is here somewhere either in first level handling or second level handling, it depends on the implementation, we enable the interrupt. What I mean by that, somehow you make sure that if interrupt once again one more interrupt of the same type kind IRQ is being processed and one more IRQ is generated. The first time maybe it is because of serial port coming, and then another maybe because of some timer interrupt happening. It doesn't matter, because if it is coming through IR interrupt controller, okay, you may have different sources, right? So we don't want to block while processing one interrupt. We don't want to, suppose you are blocking a serial port, you are processing it. We don't want to block the timer interrupt. So that is why we are enabling the interrupt inside that. Okay, so that will have a side effect. That means you have to take care of that in your processing in the handler. So latency is improved. That means because of this enabling of interrupt, we will be able to recognize, the processor may be able to recognize interrupts coming in from other sources while it is handling this interrupt. But the problem is we have a latent complexity in the implementation. Okay, but it improves the performance, it improves the latency. Okay, but one more thing you have to remember, that we are just enabling the IRQ, but we may not have any prioritization among this. Okay, whatever is being provided by the IRQ, it is handled by this method, non-nested method. There is no implicit priority given to the different sources. Okay, this is normal interrupts could block. In that case, if there are, say, suppose there are a timer device, serial device, there are so many devices connected, and we don't give any priority to them, then what happens is, if suppose you are processing a serial interrupt, though you enable this, okay, you are not enabling it immediately, so it may have some blocking of that particular. It may service the service serial port first, and then it will come to timer interrupt, because it doesn't recognize that there are two different interrupts. It recognizes that there are two different interrupts, but it doesn't associate any priority among them. So that means it will have some limitation. So one more level of complexity is providing a priority among the different sources of interrupt. Okay, so that is a one drawback, but it's a need careful implementation here, because you are enabling the interrupt. You better be careful that the context what you have saved is not mixed with the one more interrupt which is going to come. It might come. Okay, so I will be showing you an example of a nested as well as non-nested, so it will become clear to you. Okay, now what are the other ways of handling? I am going to just give you a example of this. Just major points I will be highlighting here. So this interrupts from various sources. Okay, various sources means various devices are prioritized based on their criticality of by the system designer. See, this priority is different from the priority which I mentioned about reset, FIQ, IRQ, and data aborts. That is priority of provided by ARM to different kinds of exceptions and interrupts. That is different from the different devices that are coming to a particular input like IRQ. Okay, so we are talking about a second level of priority. Different devices are connected to the IRQ, and we are trying to give priority to them so that they will have some, when two interrupts happen together, one of them will be serviced. The high priority one will be serviced. The priority level is used to dictate the order in which the interrupts are serviced. Okay, the high priority takes a high precedence. So this is highly desirable feature in many embedded systems, and method of handling prioritization can either be achieved in hardware or software. Okay, you can do it in software inside the handler, or you could do it in hardware. So what is the difference between these two? In the hardware means the interrupt controller that I talked about is helping you in terms of giving you the information about which is the highest priority. So suppose this is the interrupt controller, and then two interrupts are coming in from two devices. Based on the programming or based on the particular pin to which these interrupts are connected, the device takes a call. Okay, this controller, though both of them are generating the interrupt, it will only first ask the ARM processor to process this first, the high priority one, and then once this is serviced, then it may say that okay, if this is also enabled, okay, individually you can enable an interrupt from a source or not by the ARM processor from the microcontroller, okay, processor. So it can decide the priority based on the hardware. So that is one way of implementing it. Suppose you don't have this hardware, you have a dumb device where it it gives you a source, but it doesn't have a intelligence to give the priority. Then what you have to do? In the handler, in the first level handler, the software goes through every peripheral and then checks who is having a pending interrupt. Okay, so it will check in the order in which the individual priorities are. Suppose if it encounters the second device is the highest priority and this is not generated interrupt, but this is a generated interrupt, then it will start processing that second level processing for this particular device will happen. Whereas even if 3 and 4 are generated, these devices are generated interrupt, it won't be recognized. That means it will be pending. So it will service the second interrupt and then it will declare, it will tell the device that okay, I have serviced your interrupt. Then what happens next time again the IRQ comes, it will check, okay, this is done, this is done, oh there is another interrupt pending from the third device, so it will process it. So this is the way, this is how a software, through software you implement the priority. So this is, as you can see, that it is slower because it spends time in checking everything. Whereas if it is done by hardware, it would have done the job of identifying which device has interrupted, and it will inform that particular device to the processor as soon as the interrupt is recognized. So it will directly go to the first level handling of the device, highest priority device pending waiting for the interrupt handling. So you will see that the performance is better if you use hardware. Software in the sense it will be less complex from hardware perspective, but you may have to pay penalty in terms of executing that and identifying the device which has interrupted. So these are the prioritized level interrupt. Okay, how to handle different interrupts from different devices which have been allotted different priorities to them. Okay, this who is doing it? This is system designer. Okay, the system designer who decides the priority of different source of interrupts. Okay, these are the people who does that. So I explained about the hardware prioritization, and is other way of doing it is in software. So it needs more initialization code, of course. Okay, the startup code will be there because you have to initialize it with all the handling of interrupt and devices. Interrupt controller needs to be initialized and priorities needs to be decided. So these are the things we need to do. The advantage is interrupt latency is deterministic. What I mean by deterministic? Suppose there are two interrupts coming from one low priority device and then high priority device. Because high priority device is processed first, it can have a deterministic. So the handling of this high priority device is not dependent on the low priority interrupt happening. Okay, in this case. Whereas if there are no priority, then it is not deterministic. Why? When this high priority interrupt is coming, that time there can be a low priority interrupt just before that it has happened, and then the handling is going on in the previous case. Then it will complete this handling, then only it will come back and then recognize this interrupt. So it depends on the time at which the low priority interrupt is generated with respect to the high priority interrupt. So it is tied to the some other scenario. So it is not deterministic. Okay. Whereas in the prioritized case, it is deterministic. I hope this is clear to you. Other handling schemes, the other handling schemes are combinations of the previous two things what I mentioned. Okay. There are reentrant handlers. What does that do? Re-enable interrupts earlier in the service routine and also support priorities to reduce the interrupt. So it re-enables it and it provides the priority also to the devices. Okay, both are done. This is the combination of these two. So this is the most complex. So compared to the handling methods I have explained so far. Okay, another one is prioritize standard interrupt handler. What I mean by that? Arrange the interrupt priorities such that time taken to decide on which interrupt to be handled is reduced. Okay, so in this case, what happens is it looks at everything, and then on the order in which it checks, it will go on the service the highest available interrupt which is enabled. It will go on service it, but it has to waste time in checking them. Whereas in prioritized case, it is hardware is coming into play, and then it helps you in terms of reducing the time taken for deciding which interrupt to service. Because hardware does the prioritization, so it is much more efficient. Okay, that is what is called associating a priority. In this case, it can support priorities, but it will do it in the software routine. Okay, not through hardware support. Now, one level higher, compared to this method is grouping the interrupt handlers. That means suppose you can say that all the disk related interrupts are all grouped. Okay, USB, maybe hard disk interrupt. They are all some secondary devices connected to one source to interrupt controller, and that in turn connects to ARM processor to the IRQ. Now this whole thing is grouped, the devices, external devices, and then you can divide. You can decide all the timer 1, timer 2, okay, and multiple timers. You can group them all and then connect to the controller, okay, and then you can decide one more thing, okay. It could be UART, okay, I squared C. This kind of a different devices can be grouped together, and then they are all connected to the controller, and then they in turn. So what are you doing? We are grouping them all, and then we are giving a single priority to each of the groups. So we may say the timer is the most important. It doesn't matter which timer it is, and then second level may be commands coming from the UART or I squared C pulses, and the third level may be hard disk access. Okay, so these are the group level priorities. So this is next level of complexity. Okay, so in this session we are covering only non-nested handlers and nested handlers. Okay, very good. Now you are all ready to look at a real implementation. Okay, get ready. Fine. So this is a typical some code which is being executed by the processor. Assume that it is in user mode. Assume, can you see from this whatever I have given whether this processor is in ARM state or thumb state? You should be able to find out from the code that I have given. This code is being executed in the user mode. Okay, the mode bit of the processor is in user mode. This is the code. These are the addresses in which this code is stored in the memory, and then it is being executed by the processor. I am asking you a question whether it is in ARM mode or thumb state, ARM state or thumb state. Okay, if you have guessed it right, it is here. Okay, ARM state. Why? The difference between the instruction addresses gives you a clue. There are 4 bytes ahead, right? There are apart from they take each instruction takes how many bytes? Each instruction is taking 4 bytes. So naturally it is a 32-bit instruction. If it is a 32-bit instruction being executed, that means it is in ARM state, right? If it was in thumb state, this would have looked like this: 200, 202, 204, correct? Because all the instructions could be there except that there cannot be 3 parameters for a thumb state. So 206, it would have been this kind of addresses I would have given, and this instruction I would have given you, which would have been in a thumb state. So you have to keep your mind fresh to recognize these things. You are all now system programmers, so I expect you to be alert. Good. Now I want, maybe you can, if you want, you can freeze for 2 minutes and then try to see what happens. But this is same as what I have explained you. No need of even a break. Okay, I'll just go through that. I have already explained this in detail. CPSR is copied into, now I have specifically said IRQ mode because we know that it is an IRQ interrupt. Okay, I have told you that this is an IRQ interrupt. So no longer mode, it is SPSR of IRQ mode. It is copied. CPSR is copied into this. Please remember, when this copying happens, the CPSR is not modified. It is same as what was in the original case. Okay, that is when this particular instruction is executed, at the end of the execution, whatever is the value of CPSR, that is copied. Okay, remember that. Suppose if it was a move yes, okay, and this instruction has changed the CPSR value, conditional flags, that will be reflected in the CPSR already because it is executed. So that will be copied into SPSR. Okay, so it is safer to start execution from this instruction onwards after the service routing is serviced. After the interrupt is serviced. So there is a break in between the instructions. The way it is executed. This is executed at a particular time t, and this is executed. The next instruction is executed after time t plus some delta t. What is delta t? Delta t is the time taken for processing the interrupt routine. and coming back and executing the instruction. Though this gap is there between these two executions, the correctness is preserved by saving the CPSR values as well as making sure that all the registers of user mode registers are intact. Okay. So PC is saved. Please remember what is the value of PC which is stored. It is not this address. What is stored in the R14 of IRQ mode is this value 20C. Why? Because PC plus 8 only will be there. PC would have advanced to this address. So while saving, there is no subtraction or addition done to the value. It just saves the PC value. Okay, it is left to the handler to adjust the PC so that we start executing from this instruction. Oh, sorry, this instruction. And then, can you see the reason why this bit is there? This particular thing is there. Think it over. This corresponds to CPSR bit 5. Okay, CPSR. If you want to, this is CPSR. Okay, 5 bits. Initial 5 bits are what? Mode, right? Mode bit. Which mode? System mode, user mode, abort mode, whatever. Then this bit is for, so bit 0 to 4, 5 bits means 0 to 4 is mode bits, and bit 5 is the thumb mode, and IRQ bit is here and FIQ bit is here. Okay, 7 and 6. So bit 7 is actually thumb mode. It needs to be cleared. Why? Because all the exceptions are handled in ARM state. Please remember, all the exceptions are handled in ARM state. The processor could have, in this case it is not a different because already it is 0, because I told you that it is in the ARM state, but there is a possibility that it could be in thumb state. The processor may be in thumb state and executing some thumb instruction, and that time the interrupt happens, and that time also we have to make sure that the exceptions or interrupts are handled only in ARM state, so it has to be cleared. Please, you should keep in mind this. Some manuals and some books may not explicitly mention this. Okay, I don't see a lot of books mentioning it, but they have mentioned it in the documentation, so you have to relate to that. Okay, and then IRQ is disabled. Please remember, default this is done by the processor. The whole thing what I am showing is done by the processor. It is not executed with the instruction. It's all done in sequence. The processor knows what to do. It's all hardware, and it knows what to do when it has to service the IRQ interrupt. Okay, and then it will load the PC R15. Now it can overwrite the PC value. See, CPSR can be now cleared because it is already copied. Please remember that. Similarly, PC can be loaded with a new value because the return address where it is supposed to come after the servicing of interrupt is already copied. So we are safe now to change the value of PC or change the value of CPSR or change the value of IRQ bit. Disabling IRQ is changing the CPSR value, right? And then we are changing the mode also. A processor is changing the mode also from user mode. In our example, it is user mode. It changes to IRQ mode, and then now it goes to PC18. What is there? This is the branch instruction to handler. Okay, somewhere some handler is there. So branch to handler happens. Now let us I think all of you are clear about this. I don't have to restate that. Now let us go to handler. I want people to take some 5 minutes break, not to walk out of the class. Okay, please be there, but read through this code. Okay, read through this code and try to understand what is happening. Very good. I think I don't have to explain it all because you might have understood it already. Okay, but just for the completeness and the continuity sake, I will explain you. So, do you know the reason why this is done? What is being done? R14. Okay, this R14 corresponds to which R14? Let me draw the register banks. Okay, from the diagram you can know what I am trying to come up with, right? This is CPSR, all of you know. This is SPSR, all of you know. Sorry about this, it is P. This is R15, this is R0. What are they? Let me write it in order. R14 and R13. Where this is pointing? This is pointing at a stack. Which stack? Whose stack? Which mode it is? This is IRQ. The IRQ has come, right? So this is the IRQ stack. So this is in some memory somewhere. It is pointing at some location which has already been filled with some value, because you can make full decrement. This is the stack operation. We can, if you recall, you should go back to your previous class or look at the manual. What do I mean by FD? R13, typically we assume R13 is the stack pointer. It is pointing at a full location. That means the stack value, stack address where content is already filled into. And if you want to store anything into the stack, we should decrement it. Okay, please let me give the scenario. This is a high address. Okay, memory. This is a high address and this is a lower address. So if it is pushing, it will go downwards. Stack is growing downwards. Okay, towards the lower address. When I say lower address, I call it as a downwards. So when one push happens, it is here. The one content will go here, and then the stack pointer will come here, because it is full decrement. That means it will first decrement the value, decrement the R13, and then store the content. Okay. Now let us see. What are we trying to do here? These are the register list which is getting saved, because it is a store multiple, and then which is the base register. It is very specifically mentioned, because in ARM state it is not assumed that R13 is the stack pointer, so you can have anything, but for because it is in a IRQ mode, you better use R13, because you have only 2 registers in the bank register, so you cannot have some other register as a stack pointer, because you don't have a bank register for it. So it is always preferred and better use R13 only as a stack pointer. Okay. So now R13 is used. Okay, and there is an exclamation mark here. If you can notice it, it means when you are updating the stack, you have to update the pointer also, the base pointer. Okay, now if you recall how these values in the registers are saved, it always saves from the lower register to the higher register, and it saves from the lower address to the higher address. Please know these two are very important. Lower register to higher registers. That means lower register means R0 is a lower register. Okay, and then it always do a it's a store multiple, right? So multiple cycles, memory cycles are multi-cycle n, non-sequential and sequential. If you understand, the sequential cycle is started, so it is going to do a sequential access of memory, either for store or load. So in this case, it is going to store. So it is going to start from a lower address to higher address. Why? That is the way the memory can increment the addresses and then store them. Now tell me, okay, assume the stack is right now pointing at some 400. Okay. Now how many values are there in this register list? You can count it, 6 registers. So let me allocate space for 6 registers. Okay. I am exactly showing you what is in the stack and where it goes in. Okay, so that you understand it. So 1, 2, 3, 4, 5, 6. Very good. So next, after the loading is done, whatever the 6 into 4, 24. So I will write it in decimal form, not as a hexadecimal form. Okay. So now this is the address where the stack will come. Now tell me which registers will go where in the stack. I told you lower address. I'm sorry, extremely sorry. This is not 424. It is going towards the lower address, right? You have to subtract 24 from there. Okay. So please remember that it is some 300 something. Okay. It is not 376. Okay. Let me be specifically in decimal. Okay. So it has gone below in the lower addresses. It is not increasing addresses, lower address. So 376, correct? My arithmetic is correct, I suppose. So from 376 to 400 is the increasing address. So in this place, as you are correctly thought of, R0 will come here, R1 will come, R2 will come here, R3 also here, then R12, and then our friend R14. Why I am calling it as a friend? Because this is the register which is going to take me back to the original code. So this is my friend. Okay, good. So this is how the registers are saved. Okay, by executing this instruction. Clear? Okay. I am not going to rub this whole thing because we will lose other things. So let me. Okay, I can't write. I thought it is read is written by me. Okay, good. Let us see. Now tell me, cause what is happening? It's the actual service routine. You can call it as a first level or second level, whatever you call, no problem. But actual processing of that interrupt is done here. It is another function call. So you remember BL, what does it do? It's a branch with link register, right? That means it is now currently, it is executing some handler, maybe it is in 1200 address. The handler is started, okay. So if this BL may be somewhere in some other address, okay, maybe some 1300. So handler is somewhere, okay. It has to PC has to go there now. Please remember, it came from here. It came to vector table. From vector table, it came to the 1200. Assume this is the address of the handler. This code is located in 1200, and from there it is now going to another place which is 1300. Assume, okay. You can see the flow. Please remember where it is supposed to come back. Now it comes from here to this place. Now someone has to store this address, right? Who does it? Because you are executing a BL instruction, automatically the R14 of IRQ saves the address, this address. Assume if it is 1200, this will be 1004, okay, 1204, this instruction. This will be 1208, right? This will be 1020C. So R14 now will have the value, okay, let me write it. Can I write it here? Write it, okay. Oh shoot, I'm sorry. I don't know if I can go back. Okay, let me, sorry about that. So we have, okay, so let me recall, this is 1200, okay. I told you that this is, maybe it's good that your board has become clean now. So my memory is okay, it is a short-term memory, 1300, okay. This happens to be 20C, okay. Now let me draw the stack. I don't know whether I mentioned 300, I think, or 276. Okay, I said no problem. Okay, this was originally R13. Okay, R13 is here. Okay, this is R13. This is R14. Now this is the full location. Address is moved. Okay, stack is. I think it's a good recap for you. Okay. Now how many I have given? 1, 2, 3, 4, 5, 6. So R0 comes here, R1 here, R2 here, R3 here, R12. Okay, I will make sure that I don't erase this. R14. Now tell me what is the value here? Maybe instead of writing, okay, I don't go there. I don't want to go here. Okay, here what is the value? You know, it is 20. What is that? 208. Why? Because originally R14 was having 20C. Okay, when the handler came at this place, it has just saved the PC value. Originally it had a 20C. Okay, after that this instruction, this is R14, right? We are subtracting -4 and then writing into that to R14. So this value has become 208. Now it is holding the address to which the processor should go back after the handling is done. Understood? Now this 208 is after this execution, okay, it has come into the stack. 208 has come into the stack. Now this R14 is free to be overwritten. Doesn't matter because you are not bothered about the previous content because we have the copy of it here. So when the processor executes a branch with the link, automatically it is in IRQ, it is executing this. So it sees R14 as its own IRQ bank register. So it will write the address to which it is supposed to come back, that is 120C. Please follow me carefully. Here the processor, okay, gives you exact PC value to which it is supposed to come back after this execution. So 20C is there in the PC and automatically that is stored in R14. So you will see 120C here. Okay, and then assume the PC is now loaded with a new value which is 1300 where the handler is. So PC is here. Now R15 is here. See now R15, you see the flow of R15. What all has happened to R15? Initially it was here and then it became 18 and then it became 1200. Then when it executed this BL instruction, it has become 1300. So R15 is keep on changing. Please remember R15 is not banned. So that is only one copy of R15 is there in the processor. So it is being used by every mode. Okay, there is only one R15. No, don't mistake it that no, that R15 is also banned. There is no R15 in the other banks. There is only one. So R15 keeps on changing. Now, but you don't have to worry now because from here, if you want to come back, if you execute an instruction which copies PC with a value in R14, okay, it is enough. If you execute at the end of the ISR, if you execute the instruction which is called move as PC to R14, it will copy this 120C into PC. PC will come back here. You agree? So now what happened after the service routing is done, we have to put this instruction move as, okay, PC comma R14. So it will come back to this instruction. Now what will happen? Now it's a very interesting part. LDM FD, again same logic. Okay, the stack is same. No, you cannot have a different stack operation. And then R13 happens to be the same. But you may wonder whether R13 is modified. It could be. Suppose if there was a BL inside, you have to save this. No, you should take care of saving the value of R30, R14 there, and then that would have overwritten the previous value, and then it will come back. But in our case, assume there is no BL executed. So R13, if there is no stack operation done here, if it was done, it should be restored. Okay. Please remember any subroutine, if it is touching the stack, okay, before entering the subroutine, okay, after entering the subroutine, suppose after entering the subroutine, it is pushing something into the stack. Before leaving the subroutine, it should pop that values. Okay, please remember how many words are pushed into that. That many words should be taken out. So in this case, we can assume either the stack was used or not used, but doesn't matter. When you come back here, the R13 would have come back to the previous value. Okay. That is what is assumed. That means it is pointing at the location where last thing was pushed into. Now this LDMFD is loading how many words? Again 6 words. Okay. This comes to R0. This is copied back to R1. This is copied back to R2. This is copied back to R3. This is copied back to R12. These are all correct. But you may wonder, in this case, it is copied to PC. That is because we directly want to go to this location because effectively 208 is the address which is stored. So this is where the PC should come back after the handling is done, because at the end of this instruction handling is done. So now processor will come back. Now please see this. There is one second. Please see there is one caret symbol here. If you recall, I mentioned that when you have a destination register, a last destination register as a PC, and then you also have a caret that multiple copy, in that you have mentioned this, then automatically the processor, while assembler looks at it, it will check the particular bit in the code, encode it, and then the processor automatically copies the SPSR value. I didn't talk about SPSR at all so far. So SPSR was having the previous value of CPSR, right? Originally during this time it was copied into this. So when we come back from the handler, this SPSR is copied into CPSR, okay, and R14, which happens to be, say, while copying into R15, it is not taking from this location because this is no longer valid. It would have been corrupted also. This is what I call it as corrupted because of the BL instruction. This R14 is no longer having the old value. So it has to take from the stack only and then directly copy into the R15. Okay, please. That is what is happening here. It was originally saved from R14 to the stack and then copied from stack to the R15. So that is what is happening here by directly saying PC here. And then along with the PC, SPSR is also copied. Now what do you get it? You get the original mode, user mode. You get original conditional flags that was there when this instruction was executed, and then R15 also comes back to this. Now you see that from the user perspective, when it is this instruction is executed, now it is after coming back, this instruction is executed. It doesn't see that there is something has happened in between. That is the job of the handler. You have to make sure you don't impact anything that was done originally before the handling was executed. Handler was executed. Understood? So this is the simplest code I mentioned. In that itself, I took so much time to explain you. I hope you understood this because next is going to be a little more complex. So I wanted to spend more time here so that you understand this fully. Okay, very good. I am ending this discussion now. So let us just see, completeness sake. IRQ handler example assumes IRQ stack has been already initialized. Okay, that because we are using the stack to store our values. These two instructions are using the stack. So stack should be initialized. R0 to R3 and R12 are preserved because, okay, you may wonder why am I saving that. There is a reason. Normally, a C convention, these registers are used for parameter passing, and normally they are scratch registers which need to be preserved. It's not that you don't have to preserve other registers, that they need these are compulsory, but you may save the other registers also if you are using them inside. Okay, that is the job of the service routine. So I will talk about this later. Okay, don't bother about on-prem procedure called standard right now. Just for completeness sake, I mentioned it. So R14 holds the return address pointing at the instruction next to the last instruction completed. Next to the last instruction, okay, because we have modified the R14 value. So next to the last instruction completed. This is the last instruction completed. It is pointing at this instruction and it comes back. Very good. I hope this is pretty clear to you. If you don't, please listen to this lecture again because this is very important for you to understand the next nested IRQ handler. Okay, because that is going to be much more complex than this. Okay, very good. So it comes back now. Okay, now non-nested handles and services in individual interrupts sequentially. High interrupt latency cannot handle further interrupts occurring while an interrupt is being serviced because we are not enabling the interrupt in between. Okay. Did you see that it was enabled anywhere in the previous code? We are not changing the CPSR IRQ value at all, I bit at all, right? We are just saving that and then going to the handler mode and then we are servicing it. So we are not enabling the interrupt inside. Advantage, relatively easy to implement and debug. Disadvantage, it cannot be used to handle complex embedded systems with multiple priority interrupts. Okay, understood? You are all ready for the nested IRQ handler? Good. So you have to pay a lot of attention here because it's a little more complex. Don't worry about this particular flow diagram. Okay, it is very simple. I'll explain. So interrupt is coming. The same IRQ interrupt is coming. Okay, but the processing is little different in the handler. Okay, I am entering the handler now. I am not going to explain any more about what is happening before. This is the interrupt handler. Okay, so enter the interrupt handler, save the context. Okay, then service the interrupt. That means what? This is the first level that I call the BL service routine. It may be a first level handling, and then it will whether check, okay, inside this function it will give whether you need to do a second level processing or not, okay, whether second level processing needs to be done or not is answered by this particular first level. Typical example will be the serial port command I said. So every character you don't have to do the second level, only when carriage return is given you have to do the second level. So suppose some in the first level interrupt handler you are checking whether the character received is a carriage return or not. Okay, if it is a carriage return, then you may say that yes, I need a second level processing now because one complete command is received fully. So that kind of a thing is happening in the service routine. Okay, so prepare stack. Now, if the interrupt service routine is not complete, that means second level processing is required. Then what happens is it is switching the mode. Okay, from IRQ mode. Okay, I will show you in the next example. It moves to a system mode. So it moves to another mode and then it prepares a stack and then copies the values from the IRQ to that new mode. I will tell you why we are moving to another mode, and then enabling the interrupt. Once we enable the interrupt, that means one more IRQ interrupt can happen. Okay, that means after this point, another interrupt can come and then the same code can be executed again. Okay, no harm because we are doing something in between to make sure that the original content is saved, so that when you go back from this handler, okay, you may get another interrupt and you can service it. Okay, it could be IRQ interrupt, it may be serviced. Okay, so how to do that? That is what we are trying to now see in terms of implementation. Okay, let us complete this flow. Okay, so I will explain you this. Okay, another stack is built in another mode, and then we are copying from the IRQ mode, enabling the interrupt, and then if the frame copying everything is done, then complete the second level service of interrupt. That is, this is the second level handling. Okay, once the second level handling is completed, that is the command is given, and then you have done the job of the second level, and then you go back to the original task. Okay. So one thing you have to remember, when we enable the interrupt, we are not going back anywhere. Okay, it is continuing here. Only thing is, because of enabling the interrupt, the control can be taken back to IRQ handler again. That means it can go this code, whatever code this second level interrupt processing is happening, it will be interrupted. See, originally user mode was there. It was interrupted and it came here, and then we came first level. First time you came here, and then we saved all the things, and then we enabled the interrupt, and then we are processing. We are here. Now during this time, one more interrupt can come, and this can be interrupted, and then another interrupt can come, and then it can enter the handler again. So please remember the interrupting is happening to the core which is being serviced. Okay, in the second level interrupt handling. The original user mode, we are not going back to the original user mode because that is not more important compared to servicing the interrupt. That is always there. But we want to keep the processor open to see whether any other interrupts are coming in or not. That's why we are enabling it intentionally. That's all. Okay. This should be back of your mind. It should be there. And then we restore the context and go back to the user mode. Okay, good. I hope this much you understood. Only thing is we are enabling the interrupt inside, and then before enabling we are doing something. Okay, I will tell you what we are doing. Now is the example. Okay, please be ready. These are all some code, some constant which you can define. Okay, please remember, you don't use the same syntax for our ARM sim simulator because some of them may not work, because this is taken from the book. So you may have to change this code a little bit, as I explained in the earlier cases. .eq, then this command, this constant, and then followed by this. So I am taking from the book so that you can always go back to the book and then refer the same code. So I am explaining the same piece of code that has come in the ARM Systems Developers Guide. Okay. So let us see what are we doing. This is a constant. We mask the lower bit 5 bit. Okay. CPSR lower 5 bits are the mode bit, and then this is the SVC mode. This is a supervisor mode. Okay. We are going to supervisor mode. Okay. And then in between for processing, further processing, and the I bit is 80 because I told you, the 7th bit, which happens to be the I bit, which we are using it to enable it. Okay. And then this we have already seen the code. We are subtracting 14 from the R14 and then saving it back. So this is the code it is supposed to go. And then this also you have seen already. We are storing the same R3 to R0 to 3 and R12 R14. This also I have explained you earlier. Nothing different. And then we are servicing interrupt. We are reading the device and all that. And then okay, some code, piece of code. Don't worry about what is being done. It is only just reading from the serial port means we are reading the character and all those things. Very device specific. It is nothing too specific to the particular handling. It is very device specific. It is nothing to do with the scheme. Okay. So then we are having a branch to read schedule flags. So is it safe to execute this instruction now, BL? Yes, because R14 is saved. So the original user program return address is modified by -4 and then it is saved also into the stack. Now we are free to use this BL instruction by overwriting the R14. R14 of which mode? IRQ mode. Please remember we are still in the IRQ handler only. So I think this piece of code you are able to understand, I presume. Okay. I hope I don't want you to have any doubts on this piece of the code. Now please don't be shocked with so much of code. I will explain everything. Okay. Another 15-20 minutes I will take. So this is some constant design. Okay. Constant is defined. Okay. That is is a hash define of C. If you know it is defined as C, then we are adding C. Okay, sorry. Frame R0 is defined as 0, and then frame R0 is added with 4, and then R1 is defined as 4. So basically, we are recursive definition we are doing. We are using the definition of this to define this, and this constant is defined using this value. We are defining this constant. So basically, this is a value 0. This is 4. This is 8. This is C. Like that, it goes. So effectively, these are all the different register values. Okay, they are nothing but R0 to R15. Okay, but R12 is there. Then we are using PCR. Okay, and then R13 is not saved because R13 is a stack pointer where we are using the we are using the R13 to increment and then store the values in the stack. So we should not save the R13 inside. Okay, so this is the order in which they are saved. Okay, these are a constant used for accessing them. So don't worry about this definition. This is only a constant definition. But I will explain in the source code. Then you will understand it. So LR is a link register which happens to be R14 of IRQ. Then this is the PC. Okay, R15 value is going here. It's not actually R15, but the original R15 which came from the user mode. And then this is nothing but a frame size, total frame size. Okay, don't worry about this. Okay, so I hope this constants you understood. So let me erase it. Now let us see. See, before coming here, what did we do? We call this function. Okay, the BL, and then it has come back. So after the BL, this code is there. Okay. So it is a continuation. Okay, I have put it in a different slide. So after BL, it comes here. The control comes here, and then suppose that routine is returning some value in R0. It returns some value in R0. Okay, if it happens to be non-zero, okay, not equal to. If you are, I hope you all of you are able to read the instruction from. Okay, LDM not equal to increment after. Okay. It's a load instruction, load multiple instruction with respect to R13, okay, and then it is restoring the values when R0 is not equal to 0. See, it is a very specific to the implementation. Okay, in the previous case, okay, if this routine says that, okay, not this routine, the read schedule flag says that I don't need any second level processing at all, okay, then it will return a value which is not equal to 0, okay. Okay, if it is 0, the second level is servicing is required. Okay, so come back with that kind of understanding. Now it can go back to the original user program by executing this instruction. This I have already explained you, because prior to this STM of this is done. So stack will be having those values which I explained you earlier, the order in which they are stored. So I will explain now also, because you need it for this particular. Okay. Okay. Now let me draw the stack. Which stack? IRQ stacks. Okay. Earlier R13 of IRQ was somewhere something. It doesn't matter which address it is. Okay. It is load pointing at. I'm sorry about the straight line. Okay. My control on the mouse is not good. So R13 will be pointing here. This is IRQ's R13, and this is the original saving, okay, which we have just now saw. These are the values. Very good. So I don't have to explain this. This is the return value. Okay, I will modify the return value. Okay, so I will write it as a return address. Okay, actually it is R14 value which is copied, but it is a return address. Okay, let me write it as R14. Okay, which was subtracted by 4 so that it goes back to the user mode. Got it? So this is the status of IRQ stack right now. Okay, so if there is no further processing required, it will execute this instruction. And IRQ mode has got a SPSR. Okay, IRQ has 2 registers, you know, SPSR, which happens to have the original value it should have. Okay, so R14 R13, it can be anything. So it goes back by copying, because I have put a character. When this copies this into CPSR, and then it copies this value into PC, so it goes back to the original code. Okay, now we are not interested in that part of a discussion. Okay, we are interested in something else. Okay, that is not. Sorry. Okay, so this is stack is there. Okay, this we need it now. Okay, I'm sorry about this. So this is R14 return address. This is R12, R3, R2, R1, R0. Okay, I will not erase it anymore. Okay, so R13. Now see, assume we are coming here. Okay, this NE is not true. That means this value is 0. So not equal to is not true. So the control comes here. You know that it is a conditional execution. Please remember, I don't have to explain this thing. Load LDM will be executed only when it is not equal to. Otherwise, it will not be executed at all. So MRS will be done. What is MRS? Very simple. Status to R register. So now the SPSR was there originally, right? This SPSR is whose content it is? This SPSR. This is the IRQ's SPSR. We are in IRQ mode. This is the original CPSR value of user mode. Okay, that is here. Now this is copied into R2. Now you may wonder, how can you overwrite on R2? Okay, correct. I told you that you should not overwrite on any register without saving it. Please remember, you have saved it. R2 is saved in the stack. So we are free to overwrite R2. So SPSR is copied into R2 because you have to use the MRS instruction. We can't access the SPSR or CPSR directly. So it is fine. I hope this is understood. Now what is happening here? Move R13 to R0. Okay. So again, IRQ mode, there are how many registers? 2 registers, R14, R13. Okay, this R14 is already saved into the register, stack here. Okay, IRQ stack is already having it. Okay, now this R13 is currently pointing here. That value, whatever is the value, okay, we are writing into which register? R0. R0. Okay, maybe I should put R2 here, and then the value is here. Okay, value goes here. So R0 can also be overwritten. Can it be overwritten? Yes, of course, because R0 is here. We have saved it. So we can overwrite with a value from some other register. I will explain you why I am copying R13. Right now you assume you understand R13 is copied. That means what? Wherever the stack is pointing at, okay, is copied into R0. Very good. Now what happens? Add R13 with 6 into 4. Okay, who does this 6 into 4? Assembler would have done it. Okay, it would have made 6 into 4 as 24. Okay, it is given like this so that we understand it. As a normal human being, we don't know if suddenly 24 is put, we will question why 24, right? So you see 6 registers were pushed into the stack, and you know that it is execution is in ARM state because it is the exception handling. It will be ARM state. There is no question about it. ARM state, and then it would have taken 4 into 6, that many 24 bytes of location. Now when we add R13 with this 24 and write back into R13, what happens? R13 goes back to the original location. Please remember, R13 goes back to original location. What are we trying to do here? We have moved all the values into the register in the stack, and then moving back this R13 into this. Now you may wonder, oh, what happens to the value in the stack? It is lost. No, it is not lost. It is in the memory only. Okay. Only thing is R13 is now saying that I am the stack is at this location, and if you want to push anything, please go ahead and then write on this. Okay, if you want to and if you can. But actually speaking, we have not restored this value into some other place. These values are very important. Okay, because these registers values are in the stack, we are overwriting these registers. Okay, but the R13 is now gone back. But please remember, we are inside the IRQ handler, and we have not enabled the IRQ interrupt yet. Okay, it is not enabled. Default it is disabled on entry. So there is no possibility of another interrupt coming while we are executing this code. So we are assured of no one else coming and then trying to push something else unless you want to push something into the code here itself, because the control is here. IRQ cannot give the control to another IRQ handler to come and modify the value of R13 by pushing something into it. Please, you should have that in mind. But does it prevent from FIQ happening? No, because IRQ is a lower priority than FIQ. During this time, okay, FIQ is enabled and FIQ can come. FIQ will be serviced, but remember that FIQ module has its own bank register and its own R13 and R14. So see, these interrupts will use this R13 R14 automatically, but if they want to use any other register, they will save it and then use it. They will stay in their stack and use it, and then they restore it back and then come back. So they will save it in their own stack, FAQ stack. So if FAQ happens, it will not be a problem for us. These register values will not be corrupted. It will be, you will get back. Okay, even if it in between it goes to FAQ and comes back, no issues. So please remember that in mind. And then now we are moving the R13 up, but we have not copied the values from the IRQ stack yet. These R0, 1, 2, 3 and 12 and 14 are still there. They are very valid. They need to be copied. But we are right now just advancing the R13 for some reason. Okay, I will tell you later on. Okay, now, okay, take it from me. We have changed the R13 value now. Okay, and I am giving an assurance that our IRQ will not come because IRQ is not enabled now. because as soon as the processor recognizes the interrupt, it has disabled the IRQ interrupt. So unless we specifically enable it, it is not a issue. And then now what is happening? CPSR. What is CPSR here? Is moved into R1. Okay, please remember the CPSR is currently has some value, correct? It will be, and while the processor came into IRQ mode, it modified the CPSR. If you remember, you recall, it made this into IRQ mode. That is why we are seeing the IRQ registers. So it is currently saying that the CPSR mode bits are saying it is in IRQ mode. Okay, and then it says IRQ is disabled. The I bit is disabled. Okay, that means 1. It is set means it is clear, it is disabled. Okay, I think that is the convention. So we are not. So this is the state of CPSR now. Okay, original user mode CPSR is in SPSR, correct? Which is there, which we have copied into R2. Okay, now original user mode CPSR is here. Okay, you have to keep track of that flow, because we copied the CPSR into R2, so that SPSR was having the original CPSR value of user mode, so that is now here, and the CPSR is currently saying that I am in IRQ mode. Of course, it is in IRQ mode. So now that value is copied, CPSR is copied into R1. We can copy into R1 because R1 is old value of R1 is safe. It is safe, so no problem. We can overwrite the R1, and then R1 is masked with the lower 5 bit. Okay, we are just making sure that the 1F we are big invert. If we do the original value of CPSR, we are only you are interested in only changing the lower mode bit of the CPSR. Okay, so that is masked, and then we are Ring it to the SVCD. Basically, the R1 this is the R1. Okay, the mode bit we are changing into, say it is in to SVC mode. Still the processor has not moved to SVC mode. R1 is modified so that we can write that R1 value there. So that is we are changing it to SVC mode. Okay, 1 second, and then right now what we do, you see, we are still not enabled IRQ interrupt. Please remember. So SVC mode we have made, and then we are writing, see, that value into CPSR now. Okay, now this is a very crucial instruction which you should understand. Okay, I need space for this, so I need to be careful that I don't by chance erase everything. Okay, okay, so where are we? We came up to this point. Okay, we have changed the, in R1 we have made it at SVC mode. SVC is another supervisor mode. Okay, we are going to that mode now, and if you recall, SVC mode also has its own R13 and R14. Okay, supervisor mode has its own R13 and R14 SVC mode. You should remember that. Okay, so we are now on executing this only control flag. We are writing that into CPSR. Once this instruction is executed, now it has come to SVC mode. Okay, so no longer the original IRQ this mode registers are visible now. This is not visible now. Okay, and because of that we will not be able to access the R13. That is why we modified that value of R13 prior to coming into SVC mode, because we know that once we get into SVC mode, we will have the visibility of these registers which belong to our SVC mode, and we won't have the access to the IRQ mode registers. Even the SPSR of the IRQ mode we will not have the access. That is why we copied them into R2. So you should remember all these values. Okay, so let me now erase all this now. Okay, I need space for constructing a stack of the SVC mode. So it will take another few more minutes, I hope. you will learn this fully, okay, then anything you can understand, okay, any handler. So I am going to now you should keep in mind that we are now into SVC mode, okay. Now I am sorry about this straight line, supposed to be a straight line. I am constructing a stack, okay. Whose stack? SVC stack. Assume SVC, okay, SVC supervisor mode, its own R13 is also pointing at a full location. Something is there. I am not bothered about that. From that place onwards to frame size, take it from me. This is okay. 12 words, okay. This is totally, we need space for 16 words. 16 words means 16 to 4 bytes, okay. 16 words in the stack, that is the total frame size, minus R4, this is 4 minus 4, okay. 16, I am just telling you what is the values of these constants. So effectively we are subtracting 12 into 4, okay, because 12 words into 4 only we are subtracting, okay, 48. So from here onwards the R13 is brought back to some lower value. So let me painfully write this. I hope I will have space for. What are we trying to do? We are trying to create a space in the stack. By how? By moving the R13 down. That means the stack will be going downwards, right? Which stack? SVC stack. So this is 1. Let me no 1, 2, 3. Okay, 4, 5, 6, 7, 8, 9, 10, okay, 11, 12. So I said we are subtracting 12 into 4, so it will come here, and then we need 4 more, okay, later on. That is the total size 16. So let me write these numbers also. So you may wonder why are we needing it, because this is to save the registers. See, please keep the context ready, clear back of the mind. We have, where are we now? We got a IRQ interrupt, we came inside the interrupt, we came here IRQ stack, and then we realized that we need a second level of handling. So before we start with the second level of handling, we called this routine, and I said that we cannot go back from the IRQ routine, we need to process the second level of handling. So during the second level of interrupt handling, we want to enable the interrupt, we wanted to enable the interrupt, but we still not enabled. So before enabling interrupt, what we did, we copied, we modified the R13 to go back to this original place, okay. Though we have the contents already in the stack which is not disturbed, and our IRQ is also not enabled, so this content will not be disturbed by anybody modifying the value of R13 and pushing something into it. And then we took the SPSR value of the R13 into R2 and R13 of R0, okay, wherever, which R13 actually, wait a minute, we mod, please, R13, I'm sorry, R13 we copied into R0, right? That was which value? It was before the addition was done. So it is this value, okay, this value. So because right now R13 is now of IRQ mode has gone there, but we are having this value in the R0 register, okay. Please remember that. I am showing this. Maybe I can use different color. It will help you. Okay, sorry, in color. Let me use blue. So this is here, okay. That R13 is here, okay. I'm sick of R13, red color. So SPSR is here, okay. Now whatever is happening in the SPSR mode, I will show it in blue so that you will have some respite from red. So now these are the status, say current state, and then we are here, okay. Now I am doing a subtraction of R13, so R13 will come here. This R13 is of which mode? SVC mode. Please remember, we are into SVC mode because we did the MSR, we modified the mode. So as soon as we change the mode, R13 if you use in the code, it will refer to the bank register of SVC. These registers, okay, R14 and R13, and its own SPSR, okay. We are not used to that yet, SPSR. Okay. So now R13 we are just modifying it to this location and then executing this instruction. Okay. Now what all is blue is the SVC mode what we are going to do. So here we are storing from R4 to R11, okay, wherever R13 is pointing at. Now R13 is pointing here, I said, because we have subtracted it, 12 into 4 we have subtracted. So we are going to save starting from here R4, R5, R6, R7, okay, R8, R9, R10. I hope I am not going overboard. R11, fine, because we are saving only up to R11. Okay, no problem. We have kept the space. We are left it blank. That means something, the earlier value was there. It will remain there. No problem. But the R13 which was here is moved here. But it is why it is moved, because we are giving a STM instruction with the base of R13. And remember that we are not giving a exclamation mark here. That means it is doing a multiple say store, but it doesn't modify the R13 value. So R13 remains here as it is, but the values get written into it from the register ARM processor to memory. I hope it is clear to you. Okay, and it starts from R4 because R4 is the lowest register in the list. I hope this is clear to you. Now let us go to another instruction. LDMA R0 from R4 to R9. Okay, I need some more space. Let me create it here. 1 second. I have to be very careful. Eraser. Okay. I'll create some space here. Okay. Okay. See, you try to understand this instruction now. We are here. Okay. LDM means what? Load. Increment after. Okay. Now, with respect to base register R0, what is R0? R0 is this R13 value which happens to be this value. I told you. We saved it earlier, right? So this value, this is actually the memory which belongs to IRQ. But see, even though you are not in IRQ mode, nobody prevents you from accessing the memory which belongs to the stack, IRQ stack. Only thing is you cannot access the IRQ registers in the SVC mode, but you can access any part of the memory, right? Here we are not assuming some protection against some mode and all that. Okay, so we will be able to access this content, the stack content, though IRQ registers are not accessible. That is the reason we copy that R13 value into R0, which is visible in the SVC mode. Okay, so now actually we are copying from the IRQ stack. Okay, though IRQ in the IRQ mode register R13 is pointing here, these values are still there in the memory and we can copy them. Now where are they coming to? They are coming to the registers starting from R4 to R9. Let me draw that. R4 to R9. Okay, let me, for the simplicity, R4, R5, R6, R7, okay, R8, okay, R9. These are all the registers we are trying to now overwrite with. Okay, from this we have just one-on-one copy. So R0 will sit here. You have to keep in mind it is copying lower register to higher register, from lower address to higher address. How many registers are mentioned, that many words will be copied. You agree, right? So it is increment after. That means you copy this content first and then increment. So that is also working out fine. So R0 original users R0 will sit here. R1 will come here. R2, the original user mode R2 value will come here. Original user mode R3 will come here. R12 will come here. And then return address, that modified return address R14 will come here. So why are we doing this? Because we want to save it in this stack. we don't, there is no instruction to copy from one memory to other memory. So we have to bring it to the register and then move it to the memory, because both stack are in memory. Then why, you may wonder, why are we doing it? Why do you have to copy it? I told you IRQ is mode is, we are out of IRQ mode, and then we are going to enable the interrupt now. Okay, that time what will happen? Interrupt can come and then this will be overwritten. So before it is getting overwritten, we want to preserve this value because this is required. Because these are the values which will take us back to the user mode code. So before doing the second level processing, we want to get the all the value which we left behind in the IRQ mode back into SVC mode. Why are we coming to SVC mode? This is like a temporary placeholder for us, because this is SVC mode is modified. No, supervisor mode it will come. Okay, so you should remember supervisor mode will come only from reset and SWA instruction. Okay, so if it has to come from external world, it has to come from SWA instruction execution or reset. If reset comes, no problem. This anyway, whatever you are doing in SVC mode can be lost, but no other interrupt can bring the control to the SVC mode. So it is safer, and we want to enable IRQ interrupt. Okay, after while we are servicing the second level of this interrupt. So before doing that, we want to restore the values that we originally left with the IRQ stack into the SVC stack. So before doing that, we need to bring them into a register and then move it to the stack. So why are we moving into these registers? Because we have saved these registers now. R14 to R9 are already saved. So we are no harm in overwriting them. Original user mode register. These are all user mode values. Okay, we have restored, we have kept it safe, and then now original user mode values of this are brought here. Okay, I hope you are clear with this instruction. Now what are we trying to do here? I bit we are taking that, the 7th bit, bit 7, we are writing it into R1. Why? R1 is already having the original content that we copied from the CPSR, right? This R1 is still continuing to have, and there is no change to any of the conditional flags here. There is no instruction which has modified the conditional flag. So conditional flag is also consistent. So you can use the same thing, okay? But even then we are only changing the lower part of the byte, so no harm it. So we are modifying the I bit now. We are continuing the SVC mode, but we are enabling the IRQ bit. Okay, this is what we are doing here, and then we are writing into back into the MSR. MSR is a register to CPSR, so we are writing R1 into CPSR. So now what happens is we are in SVC mode, but IRQ is enabled. Please remember at this point, okay, after this execution, IRQ interrupt is enabled. That means it can effectively, if there is a pending interrupt in IRQ now, the control can go from here to IRQ interrupt. Will there be any problem? No problem, because we are not dependent on this register anymore, this stack values anymore, because we have copied that into our own registers. So please remember, these registers are still can be used by the handler, but we assume that any handler using this register need to preserve it and give back when it comes back, right? So we are not bothered about whether these interrupt register values will be corrupted, but the stack may be corrupted because R13, if IRQ interrupt happens, it will come and then push values into the stack. So a handler will come again, do the same thing what we did so now just now, but we don't bother about these values getting lost because we don't have any more dependency on them, because the SPSR is also copied. We have the copy here, we have the R13 value which we use to restore the value, so we don't have any dependency with the IRQ mode. Okay, very good. So I hope you understood up to this point now. Okay, now what is this instruction? STMDB R13 R4 to R7. Now STMDB R13, that means R13 is here. How many values we are copying? R4, 5, 6, 7, 4 values. That means it will be decremented by 4 with a decrement before. Okay, R13 will come here, and then it will copy from lower address to higher address the way you have given it. Okay, the values are R4 to R7 registers. These registers you are copying. but actually this register happen to hold R0 value of the user mode. So please see this. Now we are restoring the remaining registers which we left behind in the IRQ stack, which we brought it here to R4 to R9. So we have taken care of these registers now. It has been copied now. Good. So that is done now. Now what are we trying to do here? STR. So STR means single store. R2. R2 value, whatever is the R2 value, R2 is value is having SPSR value of original user mode, correct? So where is it supposed to go? It is supposed to go at a frame PSR. So that frame PSR happens to be this offset, okay? Let me tell you where the offsets are. This is the PC offset, okay? This is constant. I already showed you that. This is R14, okay? Where R14 value should go, and then this is the PSR. PSR is a processor status register. It could be SPSR or CPSR, okay? And then this is R12, okay? These are the places where the values need to go, okay? That is the constants are, these constants are actually giving an offset from R13 to this value, okay? So R13, this offset is added, that means we are accessing this location and then storing the value, that is address we have got R13 plus this, it will access this location, and we are storing value in R2. What is the value in R2? It is the SPSR value. SPSR value of IRQ, which happens to have the CPSR value of user mode. Please remember. So basically user CPSR has come here. Okay. Good. I hope you understood this. Better understand. Okay. Now, what is R8? R8 is holding. See here, R8 came from this location. Agree? R8 came from this location, which was R12 of the user mode. So R8 is copied into frame R12. That means R12 comes back here through the register R8. Doesn't matter. Okay. That is why we are copying R8 to storing the R8 in this location. So R12 has come here. Okay. The CPSR value has come here. Now R9 to PC. Okay, R9, what is it having R9? R9 is having the R14 value, which was modified, subtracted by 4. This is the original user mode code where it is supposed to go back to. Okay, after the service routing is done. So R14, that is the return address. Okay, R14 will come here. Okay, and then that is what is done here, and then R14 to link register. Okay. Now, where does R14? What does R14 have? That R14 is this current SEC mode R14. Okay, we have not saved it at all. We have not used it at all. But we need to keep it somewhere because we may have a branch with link and all that. So we don't want to lose the original link register value. So this is the SEC mode. Okay, R14. This is the return address. This is the return address. Okay, remember these two R14s are different. This is the return address originally to go back to the user mode, which is mapped to RPC, and this is R14 is the SEC is R14. We are just keeping it here. Okay, instead of the order, if you see R0 to R12, and then we are having a PSR, and then R14, then R15. That's all. R13 we are not saving because R13 anyway is required to, if we want to push something into the stack, we may need it. So that is what is happening here. So the whole stack construction is clear now. Okay. Now we can do a complete inter-service routing. We can have a branch with a link to some other second level service routing in this place. What will happen? It will go back. It will go to some other service routine, second level processing. It will happen. So R14 of the SVC will be overwritten with the link register to come back to this location, no problem, because this we have already saved, so that when we go back we will restore it and go back. So now assume that we have executed the second level instruction, second level processing, then we come here R13, okay, with exclamation mark, we are copying now up to this R0 to R12, okay, and then see, order doesn't matter. What you are writing here doesn't matter. the processor copies in the sequence in the memory to these values, okay, these registers. So effectively R14 now will be, okay, after this execution R14 will have the value which is here. Why? After R12 R14 is here, so in the memory, so this PSR value will come to R14 of SEC. Okay, this is the original CPSR value of user mode. So why are we bringing into R14? This is a temporary placeholder. We are copying the full thing into SPSR. CXSF means all 32-bit are copied into the SPSR of the SVC mode. SVC mode has the SPSR, right? Please remember, SPSR is a bank register. So we are copying that value. So this is now original CPSR of user mode is now here. Okay, understood? We are in SPC mode and we are copying the value of PSR, okay, into SPSR, and then now R13 will be pointing here. I'm sorry, it will be pointing to the full location. It will increment the upper, right? So R13 will be pointing here. Now we say, okay, load 2 more values also. Now what happens? This R14 originally what was there in the SVC, because we overwrote with the PSR value, so we are restoring it back, and then we are copying the PC with the return address, original user mode address, with the exclamation mark. When we do a caret mark, what happens? It copies the SPSR also into CPSR. Okay, you remember that when we execute this instruction, both PC and then R14 is copied, PC is copied, loading from memory, and SPSR is copied into CPSR, the user mode. So effectively we have come back to user mode now. Okay, actually we came out of the user mode to IRQ and then coming back to the user mode to SVC, okay, the supervisor mode. That is what is happening here. I think with this we are ending this particular handler. I hope this is very clear to you, the construction of the frame, and then coming back how we are copying back the value from the stack. You should go through this code again, draw this stack, understand every line of the code, so that you comprehend this whole thing. Okay, I have taken extra time to explain you. Okay, I hope it is useful, because nowhere you will see this whole lot of things explained in detail. So I thought I will take time to do this for you guys. I hope it makes some difference in your understanding, and you enjoy writing your own handlers. Okay, you will be equipped to handle your own handlers after this. I hope this is clear to you guys. Okay, with this I am ending this explanation. So let us go back to, I am erasing it. Let us, okay, summary is handles multiple interrupt without priority assignment, medium to high interrupt latency. Advantages: can enable interrupt before servicing of individual interrupt. Okay, I told you the second level handling is done after enabling the IRQ interrupt. What is the disadvantage? It does not handle prioritization interrupts, but so lower priority interrupts can block the higher priority, because IRQ, it is enabling IRQ, but the second level it is taking some time to enable them. So there may be a block because of that, because it is not done in hardware, it is done in software. Because first level handling is done in software, second level is also in software, but we are enabling the interrupt here, but during this time there may be some wastage of cycles, because there is no hardware specific enable priority. So with this we have come to an end of this class. It took a little longer time. I hope it is useful to you guys. Thank you very much, and I hope you enjoyed. I really enjoyed sharing this with you. Have a nice day. All the very best with your understanding. Thank you very much for your attention. Bye bye.